Dear students, today we discuss factorial designs. I am from Department of Statistics and with me my senior colleague Dr. C.D. Bhavsar. In last two lectures we have discussed analysis of variance and CRD, RBD and LSD. Now we extend our discussion to factorial designs. In conducting an experiment, we may observe that several factors are affecting any particular characteristics of interest. For example, let us take yield of an agriculture crop, which may be affected by three plant nutrients, for example, nitrogen, phosphate and potash. Now the question arises, given a population of experimental units, what is the effect of imposing nitrogen, imposing phosphate and imposing potash, etc. on field? The factors chosen again are usually at two or more levels. Thus each of say N for nitrogen here and P for potash and K for phosphate may be at two levels, making in all 2 cross 2 that is 8 treatment combinations. Now our object is the object of such experiment is to estimate the effect of each factor and to study how the effect of one factor varies over the levels of other factors. In this situation, treatments have a special structure, namely we call it this structure as factorial structure. The treatment design has to be chosen by the experimenter depending upon the goal of the investigation and availability of the experimental material and resources. The chosen treatment design is then accommodated in an appropriate error control design. Now if we have n factors each at s levels, we have s raised to power n. Here n is not, so actually this is s raised to power n treatment combinations or s factorial structure of the treatment. Such a design is called a symmetrical or pure factorial experiment of size s raised to power n. Now Dr. C.D. Bhavsar will take an example. Before that, I discuss an important property of any factorial experiment is that it allows one to study not only the effect of individual treatment factors but also the interactions between treatment factors. This is the main thing in factorial experiments. Thus, unlike an error control designs like randomized block design or Latin square design, etc., with no factorial structure of treatments, where we get sum of squares due to treatments only from treatment combinations. So in a factorial setup, we can further subdivide the treatment sum of square into sum of square due to different factors, that is main effects or interactions, etc. Now Dr. C.D. Bhavsar will take an example.
Dr. Parvinder say about when the factorial design is introduced, three factors are there, and then we have the different effects. In a factorial experiment, we have main effects and interaction effects. When the experiments involves the study of effects of two or more factors, then factorial designs are more efficient. We have two types of treatments, main effect and interaction effect. Now here we see one example how we can find the main effects. In this we have two factors, factor A and factor B, two factors at two different levels, high and low levels. Now we find how we can find the main effect for A, main effect for B. How we find main effect for A, main effect for B? See, we can see that the main effect of factor A in this two-level design is defined as the difference between the average response at the low level of A and the average response at the high level of A. Numerically, this is A is equal to, we can see in previous slides, 40 plus 52 minus 20 plus 30 divided by 2. Difference of this average is 21. So this is how we can find the main effect for the factor A. That is, increasing factor A from low level to the high level causes an average response increase of 21 units. Similarly, we can find the main effect of the factor B. Main effect of the factor B is, we can observe that this is 30 plus 52 at high level minus 20 plus 40 divided by 2, and this is how the main effect of B is, we get 11 units. If the factors appear at more than 2 levels, then we modify the procedure, since there are other ways to define the effect of a factor. Thus we find the main effects. Now interaction effect. If the difference in response between the levels of one factor is not the same at all levels of the other factors, then there is an interaction between the factors. For example, consider the following two-factor factorial experiment. Now here, previously we find the main effect. Now this is another example. We find interaction effect. Main effect is the difference of average of two levels. Interaction effect is the difference of these two levels. Now at the low level of factor B, the A effect is A is equal to 50 minus 30. 50 minus 20 is equal to 30. And at the high level of factor B, the A effect is A is equal to 20 minus 40. That is, it is minus 28. So the interaction effect is minus 29. As the effect of A depends on the level chosen for factor B, we can say that there is interaction between A and B. The magnitude of the interaction effect is the average difference in these two effects. It is, that is what we have, interaction effect AB is equal to minus 28 minus 30, which we have obtained earlier, divided by 2 is minus 29. So this is the interaction is large in this experiment. Now advantage of factorials. Suppose that we have two factors A and B, each at two levels. Denote the levels of the factors by A minus, A plus, B minus, B plus. Information on both the factors can be obtained by varying the factors on the factors one at a time. The effect of changing factor A is given by A plus B minus minus A minus B minus, and the effect of changing factor B is given by A minus B plus minus A minus B minus. That is, in the first one we change the B minus as it is, A plus is changed to A minus, and in the second one B plus is changed to B minus 1, in A minus remains as it is. So now Professor Parvinder is continue.
For example, we are taking 2 raised to power 2, where there are two factors H, two factors each at two levels, so 0 and 1. So here are total are 2 cross 2 treatment combinations. Similarly, if we take 2 cross 2 raised to power 3, 3 factors, it's at 2 levels, say 0 and 1. So here will be total 8 treatment combinations. Here that is 4. Here will be 8 treatment 8 treatment combinations in all. Now if we take this as 2 cross 2 raised to power 2, that is 4, so we denote it as, like for example, A naught B naught, or say 1. That means factor A and B, factors A and B both at first level, both at first level, and say A1 B naught, or say A at second level, B at first level. A naught B1, or simply we call it as B, that is factor A at first level, B at second level. We take generally A1 B1, or we simply write as AB. This is indication that for A and B both are at second level. Similarly, we can take for 2 raised to power 3, we may introduce third factor C. Now the treatment combinations for 2 raised to power 2 and 2 raised to power 3 are like this. The 2 raised to power 2, so this is will be first, then A, then B, then AB. For 2 raised to power 2, there are 4 combinations at all. For 2 raised to power 3, will like A, B, AB, then we introduce third factor C, then AC, then BC, then ABC. So 4 treatment combinations, and this is all 8. 1, 2, 3, 4, 5, 6, 7, 8. Now if we consider 2 raised to power 4 also, we can go for 4 factors each at 2 levels. So start from first 1, A, B, then AB, then C, then AC, then BC, then ABC. Now if we introduce fourth factor D, so then first will be D, then AD, then BD, then ABD, then CD, then ACD, then BCD, then ABCD. So how many all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So total treatment combinations are 16. That is 2 raised to power 4. This is 2 raised to power 3. 2 raised to power 2, that is 4. Similarly, if we Next go for 2 raised to power 5. That means if we introduce fifth factor also, say e, then similarly we can write for all treatment combinations for the experiment 2 raised to power 5. So now, how many first main effects are there? How many effects are there? Main effects are there. And interactions. Here it is, main effects are two, A and B, and it is given by the formula NC1. Here it is, N is 2, so it is 2, 1. So it will come out when we simplify this as, so 2 factorial 1, 1, that is 2. So main effects A and B. Interactions, that is NC2, 2C2, it is 1. So second order interaction is here 1, main effects are here 2. Similarly here, if we consider this 2 raised to power 3, so how many main effects are there? If we apply formula NC1, so 3, 1, that is 3 factorial, 1 factorial, 2 factorial. So total come out 3, that is A, B and C. Now interactions. For interactions, three, 2, and that will be 3 factorial or 2 factorial, 1 factorial, that is total 3. AB, AC and BC, the second order. And now for third order interactions. That is 3C3, and that will come out 1, that is this ABC. ABC. So main effects in a experiment of 2 raised to power n are given by NC1. Second order interactions by NC2. Third order by NC3, and nth order and so on. This will be NCN. Now if we add all these, that is total effects NC1 plus NC2 up to NCN, and if we add NC0 here, this will be NC1, NC2 up to so on, NCN and if we subtract, same as 0. So this will become out 1 plus 1 raised to power n minus 1, that is 2 raised to power n minus 1. 2 raised to power n minus 1. Now, after getting treatment combinations and by knowing how many main effects, interactions, second order, third order, etc., we use a method for calculating totals, which is given by F. Yates. Now, Yates method for 2 cross 2 experiment. Here we write treatment combination. In first column we write treatment combination. So column 1. In second, total yield from all replicates. Total yield from all replicates. And then third column, fourth, and here we write effect totals. Now for 2 raised to power 2 experiment, treatment combination is, we start from 1 when 2 factors are absent, that is present at first level, then A, then B, then AB. So total treatment combinations are 4 here. Total yield from all replicates we write in this way, 1 A, B, then AB. Here we write in third, it is 1 plus A, that is addition of first and second. Then second term will be addition of third and fourth, B plus AB. Now we divide this in 2 portions. Now that is, this is first portion and this will be second portion. In the second portion we write subtraction. Subtract A minus 1, A minus 1, and in second it is AB minus B, AB minus B. Now by same procedure we write it in fourth column. So this is 1 plus A plus B plus AB, and next, that is addition of third and fourth, that is A minus 1 plus AB minus B, and Now in third, write the difference of first two, that is b plus ab minus 1 minus a, and here it is ab minus b minus a plus 1, and in last column this will give you as grand total. And this is a, total of factor a, and this is total of factor b, and this is total of a b, So using Yates method we get effect totals. Now consider for 2 raised to power 3 experiment. 2 raised to power 3 experiment. Now we introduce here third factor, and third factor is C. So C, next interaction will be A, second order AC, then BC, then ABC. And total yield for factor C from our replicates, it is C, AC, BC and ABC. Now third column, add first two, that is 1 plus A, then B plus AB, then C plus AC, then BC plus ABC. Now subtract, that is A minus 1, AB minus B, then AC minus C, then ABC minus BC. Now for the simplicity we call it as, say, U1, call this as U2, call it as U3, call it as U4, and up to U5, U6, U7, U8. Now in fourth column, by same procedure, we write U1 plus U2, then U3 plus U4, then U5 plus U6, U7 plus U8, and then take difference U2 minus U1, U4 minus U3, then u6 minus u5, u8 minus u7. Now say let this is v1, this is v2, this is v3, this is v4, this is v5, this is v6, this is v7, this is v8. Now again for fifth column add, this is v1 plus v2, v3 plus v4, v5, v6, v7, v8, v2 minus v1, v4 minus v3, v6 minus v5, v8 minus v7. Call this as w1, call it as w2, w3, w4, w5, w6, w7, w8. Next is effect totals. This will give you the value of G, grand total. Grand total. This is effect of factor A, this is B, this is AB, this is C, this is AC, this is BC, this is ABC. So using Yates method, we can find the effect totals by the simplest way. Now we take an example. Now, considering randomized block designs with 4 replicates. Randomized block design with 4 replicates. In block first, we take K, P and KP. Here K is for sulfate of potash. Sulfate of potash, for example, and P is sulfur phosphate. Applied at 2 levels, that is 0 and 1, for a potato crop. Now, considering RBD, the yield from first block where sulfate of potash and sulfate of sulfur phosphate absent, it is 23 maybe in kilogram or maybe in different units of weights, and say in block first when we apply only sulfate of potash, the productivity, that is yield, come out as 25, and when we apply only sulfur phosphate, that is yield is 22, and when we apply both type of chemicals, the yield say come out it is 38 in block first. Now in block second, when we apply only sulfate of potash, sulfur phosphate, it is 40, when both absent, that is 26, and K only when it is 36. So when Kp is, that is both present, that is 38, for example. In third block, when both absent, 29, when only K, it is 20, when Pk, it is say 30, when P, it is only 20. And in fourth, when both chemicals present, yield is 34, when K is present only 31, P 24, 1 28. Now, so 23 is yield when neither sulfate of potash or sulfur phosphate applied. When only yield 25 is when only sulfate of potash we apply, and yield is 22 when only sulfur phosphate present, that is sulfate of potash is absent, and 38 is yield when what type of chemical we apply. For a particular crop you may consider potato, tomato, whatever we want. Similarly here it is only sulfur phosphate is available, both are absent. Here only sulfate of potash, here both chemicals, and so this is we apply in RBD. Now for the analysis, to know the, for example, if you test the homogeneity, our null hypothesis, for example, is to test the data is homogeneous. Suppose this is our hypothesis, the data is homogeneous with respect to blocks and the treatments. Now by applying Yates method, we calculate grant other factors, for example correction factor for the analysis. Correction factor is given by formula G square over N, and this is 0. We round off all these values by taking y is equal to say 29. Our correction factor come out as G square over N, that is grand total is 0. When we reduce all these values by taking y is equal to 29, and then we can apply Yates method, then we get G square over N is equal to 0, because there is G is 0 for this experiment. Then we write total sum of squares. Total sum of squares is given by formula Yij square minus correction factor. I takes value for treatment and for blocks. So this is 660 for this experiment. It is 0, that is 660. Now block sum of square is here 1 by 4 sum over j, that is bj square minus cf. This is 930 over 4 minus 0, that is 930 over 4. This is 232.50. And treatment sum of squares (1 by 4) summation I ti square minus cf. It is 198. And error sum of square, it is total sum of squares minus treatment sum of square, say SST, or sum of squares due to blocks, and that will be, that is 229.50. By putting these values in analysis of variance, that is ANOVA table, and calculating f, and then we compare calculated value of f with tabulated value. So when we write analysis of variance table, here we write source of variation, say blocks, here treatments, KP and KP, and here we write error. Here we write degrees of freedom, sum of square, mean sum of square, and the value of f, variance ratio f. For this, blocks, there are 4 blocks, so degrees of freedom, that is 4 minus 1, 3, and there are 4 treatments, 3, so 1 for this degree of freedom P for 1, and this is for 1. We divide 3 into 3 parts, and so total here it is 16, so it is 15 total. Sum of squares come out, it is, I am directly writing MSS, that is, it is 77.5, 66.0, 100, 49, and 49 and 25.5, and the value of f for this is 3.04, 2.59, 3.92, 1.92, 1.92. And tabulated, we compare with tabulated at 5% or 1%. Tabulated, it is 3.86, 3.86, 5.12, 5.12, 5.12, 6.99, 6.99, 10.56, 10.56, 10.56. And now, in all the cases, the calculated f is less than tabulated value of f at 5% or 1% level of significance. So, in all the cases, there is no significant main, no difference in significant main or interaction effects present in the experiment, because our null hypothesis here it is accepted. Calculated f is less than tabulated f in all the cases. So there is no significant difference here. Now, any question? Thank you.